Trevor from Telecom Training, and this is the third in a series of videos on fiber optic cables. If you're new to this channel and haven't seen those videos before, a link to those videos are within the description below. Now, we ended the last video talking about the angle of acceptance. Now I'm going to do a quick review before moving on. Light is sent into a fiber optic cable using a laser or an LED. When the light enters, it enters on an angle. It never enters straight down the middle of the fiber, which is the 0-degree point. It enters at an angle. And that angle all depends on the value of the core and the cladding. Now the core is 1.47 here and the cladding is 1.45. Now we are going to use these values to determine what the angle is supposed to be. So we use this equation under here. We say n1 square minus n2 square. Of course, n1 is the core and n2 is the cladding. And n1 is equal to 1.47, n2 1.45. So over here we have 1.47 square minus 1.45 square. And then of course we do the square root of the results. And what we get here is 0.24166 radians. And of course we have to convert that to degrees because we need to know the angle. So we take the inverse sine of that, which we have listed here, sine with a -1 written there. That's the inverse sine. And that is equal to 13.98 degrees. Now, if any of you don't know how to do the inverse sine, we use a scientific calculator, and I'm going to show you how to do that really quickly before moving on. Okay? Now, this is a scientific calculator. This is a Samsung S20 that I'm using. I don't know what type of cell phone you're using, but all cell phones should have a scientific calculator. Normally you have to turn the calculator horizontally to see the scientific calculator. Now what I want to do here is that I want to find the inverse sine of 0.24166. You see the two arrows in the upper left hand corner? If I click on those arrows, you'll see sine right under it says sine -1. If I click on it again, you see the sine -1 goes away. Now, what the sine, I'll click on it again. What the sine -1 means, that's the inverse. So if I click on sine -1 right now and just type my numbers in, which is 0.24166, 0.24166, you'll see right under there it says 13.98. That means it's 13.98 degrees that we're talking about. If I hit the equal sign, you see it gets much bigger. 13.98 degrees is the inverse sine of 0.24166. So here we have our light coming in, like we just talked about, at this 13.98 degrees. But we see the light stop and it changes direction. And the reason this happened is because of a change in refractive index. Light in the vacuum or light in the open air has a refractive index of 1.0. For light from a laser or LED has a refractive index of 1.0. And that light is entering into the core, which is glass, which has a refractive index of 1.47. It's like a change in resistance. You have free space out here in a way, and so the light travels faster. It travels at 300 million meters per second. In here, it's about 200 million meters per second. It's very much like if you shine a flashlight into water. You'll see that that light goes into the water, but then it changes direction. It bends. I don't know if you've ever noticed that, but the light would change direction because it's going through the air, which is free space, 1.0, but then it hit the water with it, and the water has a refractive index of 1.33. That would change direction because the difference in resistance to that light. And it's the same thing here. So what we're trying to determine here, we know it changed direction, but by how much does it change direction? And what determines that? The refractive index of the light coming from the laser or the LED, the refraction index of the core, and the angle of acceptance. So these three things we're going to use to determine this angle. Okay, we use an equation that's called Snell's law, and this is that here n1 is the refraction index of air, which is 1.0. So we have got n1 1.0, right, times the sine of the acceptance angle, the sine of 13.98 degrees. 13.98 degrees is the acceptance angle, the angle that the light came in at, right? So, and that is equal to 1.47, which is right here, equal sign, corresponding to that equal sign there. And this is N2, 1.47. N2 is this refractive index, or we can look down here. N2 is the refractive index of the core, 1.47. 1.47 we got right here, times the sine of the angle of refraction, the same sign here, the angle of refraction. We don't know this part as yet. That's what we're trying to figure out. We're trying to figure out the angle here. This angle is called the angle of refraction, and we're trying to figure this out. We already know this side. We know everything on this side here, so we're going to work this side out first. So it's 1.0 times the sine of 13.98 degrees. You just use your scientific calculator. You type 13.98 degrees in and hit sine, and you will get 0.24158. And that is equal to the same information over here. I just brought it down, right? Because we don't know this as yet. But what we do is we take angle of refraction and bring it over here, and we calculate what this is equal to. 1 times 0.24158 is equal to 24158, the same thing, right? So that would be 0.24158 over 1.47, right? This 1.47 here, we bring it here. So we just divide this by 1.47, and we get 0.1643. We just do the inverse sine of that, right? So we go to our scientific calculator again, and we take the inverse sine just like I showed you earlier. And so we just do the inverse sine of this number, and we get 9.46 degrees. And so the answer here for this angle would be 9.46 degrees. So now we have figured out the angle of acceptance and the angle of refraction. This is all important in trying to figure out what angle is this light going to be hitting the cladding, because it is important for this light to hit the cladding between the critical angle and 90 degrees. Okay, the critical angle we haven't worked out yet, but we're going to be working that out. If it doesn't come into contact with the cladding between these two angles, the light would be lost. If it comes into the cladding at an angle which is greater than 90 degrees, the light is going to go right through the cladding and be lost forever. If it goes in at an angle that is less than the critical angle, which is right somewhere up here, the light will be trapped within the cladding. So it's important for it to be in between these areas here. So the next angle that we have to figure out is the angle of incident, where this light is going to be hitting the cladding. Now we're going to be working on the angle of incident. The angle of incident, as I said before, is the angle that the light hits the cladding at. If it hits the cladding at an angle between 90 degrees and the critical angle, then it is reflected off the cladding, and it would be continue reflecting off the cladding in a sawtooth pattern like this until it reaches the receiver. That is called total internal reflection, and that's how light travels through the core. But if it doesn't, as I said before, it will be lost if it is after 90 degrees or before the critical angle. So it has to be within here. So to calculate the angle of incidence is very simple. Just subtract the angle of refraction from 90 degrees. So we have our 90 degrees here minus 9.46 degrees, which is our angle of refraction. This angle here that we just worked out, the angle of refraction. We got 80.5 degrees. So we know that our angle of is 80.5 degrees, so it will be somewhere in here. But we don't know yet if this is going to be good for total internal reflection, which is basically what I just described, when the light is reflected off one side, the cladding, until it gets to the receiver, we refer to this as total internal reflection. If it is not in this area here, we wouldn't have total internal reflection. We lose the light. It will be lost either right through here or be trapped in the cladding. The next thing we have to do now is to figure out the critical angle, and then we will know if we have total internal reflection or not. Now we're going to be looking at the critical angle, which is this angle right here. How we calculate the critical angle is very simple. The critical angle is equal to N1 over N2, which is equal to 1.47 over 1.45. This is N1, 1.47 over N2, 1.45. And you get 0.9863. You need to change this to degrees because you need the angle. So you do the inverse sine of this number and you get 80.5 degrees. Now 80.5 degrees is exactly the same as my angle of incident. Now the rules are, if the angle of incident is the same as the critical angle, you will have total internal reflection. The light would not be lost into the cladding. It would actually be reflected off and you will have total internal reflection. So your angle of incident could be the same as a critical angle right up to 89 degrees, but it cannot be up to 90 degrees. You lose your light through the cladding at 90 degrees. So the angle of incident can be the same as the critical angle right up to 89 degrees. Okay, so this would work at 80.5 degrees, so you will have total internal reflection where your light will be reflected off here at 80.5 degrees. You'll have your angle of incident here at your critical angle point right here, and you'll have total internal reflection at that same angle of 80.5 degrees, and it will just be reflected off the cladding in this sawtooth pattern until it gets to the receiver. Well, congratulations guys, this is the end of the math. There's no more math. We have done all the math equations, so we don't have to worry about that part anymore. But it is important for you to just review the math and understand how it works. And if you have any questions, please let me know. This is the last slide that we're going to be working on. This video went a little bit longer than I anticipated, simply because I wanted to keep it all together, because this particular part of the video with the math is also relatable. So I didn't want to split it up because it would be a little bit more difficult to explain it if I did. So I just want to keep it all together so I can explain it all at once to you, and hopefully that was helpful. This slide looks a little bit different, but it's basically the same idea. So let me explain how it works. Now this is the light coming in from the laser LED. It's called the angle of acceptance right here that we talked about earlier. This is the 0 point. And this is the angle of acceptance. This light came in at 13.9 degrees was the maximum. It came from 0 to 13.9 degrees is that light that came in. You notice here I have a lot more paths than before. Before it was just one. This happened mainly with multimode fiber. At the angle of refraction, when the light turns, when the light changes direction, a whole bunch of different paths are generated. This could be hundreds of paths. And these paths all go towards the angle of reflection area, right between the same area between 80.5 and 90 degrees. So you have all of these paths and they all have their own angle. Like this first one could be 87 degrees, for instance. If the angle of incident where it comes into contact with the cladding is 87 degrees, the reflected angle would also be 87 degrees, and it will be reflected off this side here at 87 degrees again, and it will continue this angle of reflection off the cladding in this sawtooth pattern all the way to the receiver at the same angle. The angle doesn't change. The second one will have a different angle, and that angle will be maintained all the way to receiver. So all of the different paths that are generated will all have different angles. You would even have direct pass right from the angle of refraction right through the receiver as well. Now, this could be a good thing where you have more paths for the signal to go through, so you have a nice strong signal. That is true. However, there's a negative side to this. Many of the paths got all of these zigzags, and when the zigzags are close together, it means that the paths are longer. Here we have a direct path, so the signal will get to the receiver really quickly. But these ones that are zigzagged would take longer, and the closer the zigzags, the longer it is. Well, what happens is that the paths that are shorter would get there first, and the zigzag paths would take longer. And this caused distortion because a lot of the signal may not get to the receiver on time, so the signal becomes distorted. Also, the next cycle may start. So a next pulse, another light pulse may be sent out, and that light pulse will be broken up the same way. But the light pulse on the fastest path may get to the receiver at the same time as light pulses from the previous paths, and this may cause an error. The receiver wouldn't be able to differentiate between what's from one path and the other path, so this will cause an error. And the longer the cable, the more errors you will get, or the faster the speed, the more errors you will get. That is why multimode fiber cables are generally quite short, between 300 and 500 meters on average. Now this issue is called modal dispersion. Modal dispersion is a very common problem with multimode fiber. Now, to get around this problem, manufacturers came up with a new cable called a graded index fiber cable. The regular cable is called a step index fiber cable. The graded index fiber cable manufacturers came up with to solve this problem with modal dispersion. And we're going to be talking about this in the next video. So, if you haven't subscribed as yet, please don't forget to subscribe so that you'll know when the next video is released. And please don't forget to click on the like button as well. It really helps. My name is Trevor from Telecom Training. Thank you for watching, and I hope to see you in the next video.